So we saw in the previous video that if you have two lists, this list is of size n and this list is of size m, right? So it was taking us order of n into m time and order of one space, right? To find common elements, right? That was the task that we had. Now, is there some way for us to reduce the time complexity, right? Is there some way? So for this, there is a data structure called a dictionary. So we know about dictionaries in Python, right? Dictionaries in Python are also called as hash maps or hash tables. There is a subtle difference between hash map and a hash table, but these are often called hash tables and hash maps. Those of you who have studied computer science would have studied about hash maps and hash tables in your data structures course. Not data science, data structures course, right? A dictionary in Python is nothing but it's an implementation of a hash map or a hash table. Now, using this very interesting data structure, what we will do is, here we are assuming that n is greater than equal to m, right? That's the assumption here. What we will do here is, we will try to reduce the time complexity to order of n, right? We will do order of n time, but we will take order of m space. So first thing you have to notice is the space has increased. The space has gone from order of 1 to order of m, but the time has come down from n into m to n itself. This is called a trade-off. What we are doing here is a trade-off. We are doing a trade-off between space and time, right? So what happens sometimes is, space is basically your RAM. Space is nothing but your RAM. Over the years, what has happened is the RAM in your computers has increased drastically, but the computational power hasn't increased, or the time it takes hasn't increased. So if you can spare some space, right? Let's assume you're sitting on an 8 GB RAM box or a 16 GB RAM box or even a 4 GB RAM desktop or laptop. You can store so many numbers in this, right? So is it okay, whenever it's okay for you to take some more space, but if reduction of time is important, right? Again, which algorithm is better depends on the case, right? If you want to reduce time, but you're okay taking more space, this algorithm is better. If you're in a world where I don't care if it takes more time, but I don't have space. Suppose you're running this code on a small microprocessor, right? On a small chip, on a microprocessor chip, right? Or on an IoT device, which has very little space. Then you be careful. You're okay. Again, depends on the application. I'm not saying this is always better than this, right? But if you have space, then this algorithm is way, way faster than this algorithm. Now let's see how to use it using hash table or dictionary. The most important part of a hash table, the most important property of a hash table or a dictionary is this. Suppose when I insert data into a dictionary in Python, you remember this, right? We have keys and values. You can put anything. For example, suppose if I have a list like this. 32, 46, 31, 22, 28. Suppose I have these 5 numbers. Okay, this is a list. And I'm putting it in dictionary D. This is a dictionary D. Okay, this is a list L. So I can insert these values. So I can insert this 32 as a key. I can take any random value. Okay, let's say I'm putting a value of 1. You can put any value here. Doesn't matter. Now I'll take the value of 46 from the list. So I'm going one by one. I insert into my dictionary. So I insert 46 and I'll put some value here. These values do not matter. Only the keys matter here. Similarly, I'll insert 31, some value, 22, some value, 28, some value. Okay, so I'm inserting the data. From my list to a dictionary. Now, the most important property of a dictionary is this. So if I have a dictionary D and if I say d.get 31, okay, this is how we query, right? This is how we query a dictionary. When I say d.get 31, dictionaries are a beautiful piece of mathematical engineering. Dictionary, internally, the way it works. So you might say, why do we have this? Why can't we just store it as a list, right? Or as a NumPy array? Dictionaries have one brilliant property. The most important property of a dictionary is, if you give it a key, right? I can directly go to the row in which this key exists directly, which means I can go there in order of one time. I don't have to traverse line by line by line. I don't have to do this. Dictionaries help me directly go to that row which has the key 31. This is the most important property of a dictionary. Property of most important is order of one search time. And how does it do it? That's beyond the scope of this course, but it uses something called hash functions. It uses a brilliant idea in mathematics called hash functions. Brilliant idea. It's one of the greatest ideas in data structures, if I have to say. Right? It uses, but using that mathematical property of hash functions, a dictionary can, whatever key you give, it can directly go to the row. And how it does that internally is beyond the scope. It uses something called hash functions. A brilliant idea in mathematics to do that. But the most important property that you have to remember, of course, if you have time, please go and understand what hash functions are. There are a lot of nice tutorials online on how a dictionary or a hash table internally works. But for now, what we only care about is this brilliant property. Is given a key, I can search whether that key exists or not. And I can get that whole row in a key in order of one search time. I don't have to go sequentially. And this is done using hash functions. This is the most important property of a dictionary. Now, can we use this dictionary to solve our problem? Right? So we have two lists here. Right? We have a list of size n. This is list 1. I have a list of size 2. I have a second list of size m. Right? n-1 and m-1. Right? Now I want to find common elements. So what do I do first? Now I'm assuming that m is greater than equal to n. So first step I'll do is I will store L2 into a dictionary D. I'll put all of these L2 in a dictionary D. But this uses some space. This uses order of m space because our input only had L1 and L2. Within our algorithm, I'm using additional space because dictionary D is also of size m, right? Dictionary D is also of size m because I have to store each of these m elements, right, in my storage. And hence, it's going to take order of m space. Now, once I've done that, once I've stored it in a dictionary, I will go through each element here sequentially. Now, I'll go to this first element. I'll make this as my query element. And I'll say, find this in my dictionary. And how much time does it take? It takes just 1 unit of time to find whether this element is in the dictionary or not. Similarly, this takes only 1 unit of time. So on and so forth. It only takes 1 unit of time. Right? So first of all, let's go step by step. Second is sequentially search L1 elements in D. Now to do this, it took order of m space, and there is one more thing that I forgot, that it took order of m time. Because you're going through each element in your L2, and inserting into dictionary, right? So what has happened is it has taken order of m space and order of m time to do that. The first step. The second step is you're going sequentially element by element and you're searching it in the dictionary. And each search takes one unit of time. So the total time for this is order of n time. So what is the total time and space? My total time is the sum of these two times, order of n and order of m, because they're done sequentially, right? First I do this and then I do this. So my total time is order of n plus m time, and my space is order of m space. Now remember, n plus m is much less than n into m. Just for example, if n is 10 and m is also 10, 10 plus 10 is 20, whereas 10 into 10 is 100. Okay, there's almost a huge difference here. Don't forget that. Now, this is how we reduce. So now finally what we have here is we have order of n plus m time and order of m space to do this operation. Now let's go through some simple code to do it. It's again very, very straightforward. I have two lists here, right? I'm taking the smaller of the lists, right? My smaller list is L2. I'm creating a dictionary here, right? As you can see, I'm creating a dictionary here, and I'm inserting each of this. This is order of m time and order of m space, right? And this is order of n time. because I'm going through each element in my L1 and I'm searching if it's there in my dictionary or not. Because this operation takes order of 1 time, my total time is order of n plus m, and my space is order of m. Very, very simple code, right? So this is the whole fun about algorithms. The fun about algorithms is how do you reduce time complexity, and how do you reduce space complexity? Because reducing them simply is sometimes the difference between life and death of an algorithm or a solution. Okay, hope this gives you some idea about time and space complexity. Again, let me be very clear here. I have not covered all the concepts in computational complexity, right? In computational complexity, what we have covered is big O notation. There is something called big theta notation. There is something called as omega notation. There is a lot of detail here which I have not covered for the sake of brevity, because whatever we have learned right now, those are the similar tricks that we will use, right? And after this section, we have some references. Those of you who are interested to learn computational complexity further, feel free, or you can pick up any textbook on data structures and algorithms. You can pick up any textbook on data structures and algorithms where computational complexity will be explained in detail. If you're from computer science background, I'm assuming that you know some of it, or probably you've forgotten some of it, but this is extremely important. Computational complexity is extremely important for any computer engineer, for any software engineer to understand and to be able to build better algorithms.